Also have
And
30
yeah, how far travel, somehow you're supposed to work out the velocity out of that. But I didn't get that yet.
Talking first off. Equation for position. The equation for velocity is the derivative of that. Equation for acceleration.
Hi. All right. We're recording, by the way.
Hey, Lucas.
We don't actually do a whole lot of pulley problems in this type of picture that we see here. This is just to illustrate what we do with tension forces when we do have pulleys. So for this particular instance, we've got two pulleys. The first thing is for us to identify what is the object. All right, neither of the pulleys are the object. The object is that mass hanging from the pulleys. So, well, and in fact, this part, the pulley, actually, the bottom pulley is actually kind of part of this mass system. When we draw the free body diagram, that's important because there's a string on one side of the pulley and a string on the other side of the pulley. And as we can see, if you're pulling on that string with 50 newtons of force, that force is transmitted undiminished on all points of the string, which means that it acts upward on this side of the pulley and upward on this side of the pulley, both sides with 50 newtons of force. So when we draw the free body diagram, this is what it would look like. You've got object, which is sort of mass plus pulley, plus bottom pulley. And you've got two tensions, because you've got both sides of that pulley with tension forces. And then that downward force is mg. And if this was in static equilibrium, you would be able to hold up 100 Newton force, holding it with, 100 Newton weight, holding it with 50 Newtons of force because of the two tensions up here opposing that weight downward. This, on the left-hand side, is a quick summary of the sum of forces. It's very uncomplicated, but you can see how you can get that same answer with your calculation. It's not a very complicated calculation area. The sum of forces in the x direction are 0 because we don't have any forces in the x direction. This is an example of equilibrium. So you see the sum of the forces equals 0, and then you've got all the forces that are actually in the picture.
Can I ask a question? Remember like physics in high school, you count like the strings across, like including the one you're pulling?
Yeah, you know, that always confused me. So,
Because that doesn't work for this one,
yeah,
because of where the rope is attached.
yeah.
It's attached on the pulley.
There was too many like, but in this case, and if in this case, and I just was like, I just got to draw a good picture. That's what it comes down to, and it's that's why we don't do a lot of pulley problems in here because it just can get overly complicated, and there's way too much to cover. So yeah, I remember that from high school too, and I don't remember all the silly rules, but I would say just make sure you draw a good picture and identifying what is the object of interest is kind of key, and then go from there.
How do you know it's 50 in this situation?
Oh, like they would have to, like say the question was, if you pulled on this rope with 50 newtons of force to hold up a weight, what's the biggest weight you could hold up? So this part you wouldn't know. And then you'd be able to look and say, well, that 50 newtons of force transmits to all parts of the rope, so I know this tension is 50 and this tension is 50. All I need to solve for is what is mg. So that's how we get that T plus T minus mg in our sum of forces equation. Rearrange, and you've got 2T plus mg, and since 2T is 2 times 50, then you get your mg.
Would it be the same as saying like the force times 2 pulleys?
I don't know that it always works that way. Again, like I remember a lot of exceptions to the rules with pulleys, and so I don't like sweeping generalizations when it comes to pulleys because I'm afraid that whatever I say is probably wrong in some instance.
Just like the number of times the rope wraps around the pulleys.
Yeah. Your book doesn't even go into it, so if you guys want to research pulleys on your own time, you're welcome to, but I do remember that it gets very complicated very quickly. Okay. Here's another classic physics example that relates to no problem ever. The elevator example. Why are you standing on a scale in an elevator? I don't know, but apparently it happens all the time in physics land. So you can evaluate what happens to your body in an elevator quantitatively if you happen to take your scale, your bathroom scale, into the elevator with you. There's things that we feel qualitatively. When you go up, the elevator goes up, and you feel heavy. And then when it goes down, and you're like, I feel like I'm floating. Well, if you wanted to quantify that, you could actually quantify it by taking a bathroom scale into the elevator. So that's why we have these silly problems. Okay. So the free body diagram for this guy, there's the normal force from the scale pushing up on his feet, and his weight pushing down on the scale. This is not apparently obvious, but the normal force being exerted upward is exactly what the scale reads. The scale is reading how much force it's pushing up on you so that you don't break the scale. Okay, and that normal force based on this picture, if he was just stationary, would just be equal to his weight. But if the elevator is moving, so we've got, simplifying here, we've got normal force up and mg down, and let's say that elevator is moving downward, so the sum of the forces in the y direction, this is the part where we write ma, right? And in the y direction it would be may, but looking at the direction of that A arrow, it is down, so I have to add a minus sign right here to acknowledge that. Okay, then I'm going to put in all the forces that I see. So again, this is the stuff that's specific to our free body diagram. We have the normal force, which is up, and minus mg down. And if you wanted to know what the bathroom scale read, you'd be solving for the normal force. So in this case, rearrange it, and your normal force would be your weight, mg, minus the force due to your downward acceleration. So your mass times the acceleration of that elevator. So pulling the m out. So the faster the elevator moves, the less the scale is going to read, right? Because the bigger that A value is, the smaller this whole number is. And if your acceleration equals gravity, basically someone snips the cable and it just falls, this whole term goes to zero, right? You can't exert any force on the bathroom scale if you're in free fall. So the bathroom scale would read zero wave.
Just to make sure I'm clear, like the mg and the may, the m would just be like 120 pounds, 160 pounds.
Not
whatever you
pounds,
weigh, right?
not pounds. Pounds is weight,
Kilograms?
kilograms.
And then g would be gravity,
Yeah.
which is 9.81 or whatever.
Yeah. Any other questions?
So the mass and acceleration, that's the mass of the person in the elevator, not the elevator.
Not the elevator. Yeah, so in this case, we're interested in the forces acting on the person, so the person is the mass. Okay. All right. Spring examples, I think we kind of already went through spring examples on the board. Okay, so I'm gonna skip this one. We're not actually doing springs in this chapter, so I'm gonna skip this slide. Okay, so those are like the main examples of force kinds of problems that you're gonna see. And the goal now is to help you get used to setting these problems up. All right, so you've got your worksheet. And there's a whole lot of examples that are in the worksheet beyond what we're just gonna do here in class. So what I'd like to do is, let's see, to actually go over these problems, but I'm gonna give you guys maybe a half an hour to just work in your groups on any of the problems that you want to hit, you know? And you don't have to get to an answer, but I want you to practice doing the setup. So get through as many problems as you can where you do your free body diagram and you do your sum of forces. Once you get that set up, everything that follows is just algebraically manipulating the equations, okay? But if you get these two things set up correctly, everything follows very nicely. This is the hard part. So, work through whichever problems you guys want to work on in a group, and after half an hour we can check in, and if there's problems you guys are struggling with, we can do them on the board as a group. And these are the ones that I definitely want to make sure you understand how they're due. Okay? So I guess maybe focus on at least doing the setup for these 5 problems, because these are the ones I'm going to go over. And I'll just check in half an hour and see where you're at.
Does it ever cause any problems like me looking at X, I kind of like to look at them.
Never read them.
You are welcome.
They're scary because like it's not like a sled. Like once you fall off,
There are times when you won't be able to
flip or
solve
hit
the
something.
Well, then I'll stick with that, because I just wasn't sure, just because looking at the conception, I thought, if I saw that, then I'm just literally looking down the X, Y axis. It seems to make my life, but I had a feeling that there'd be issues when I did that, but it might be.
There's some kinds of problems where if you decide to just use regular science,
They are
you
faster
won't
than
actually
slugs because they only
solve
have
the
2.
problem.
It's like so
But sometimes you can, you will find that there are very few problems where it matters very little which way you choose.
exactly. Now you got
There's a
like
lot of problems where this makes life a lot easier.
yeah, pretty much.
Alright.
At the bottom, learn with students.
You know, the board thing, they have